Hello, my name is Yan Zhao. Today I'm going to introduce the KDDCup 1999 using different machine learning algorithms and error analysis technologies as a big data final project. First, let me introduce what the problem is. So we want to develop a software that will detect network intrusions that protect a computer network from unauthorized users. Well, the intrusion detector learning task is to build a predictive model to distinguish between bad connections and good connections. So the bad connections we may treat as the attacks, and good connections is just the normal connection. So the raw training data is about 4 gigabytes of compressed data that from 7 weeks of network traffic, that are about 5 million connection records, and the test data is 2 weeks that yield about 2 million connections records. So it's a really large data set that here I may use the R Hadoop to solve this problem. And further in detail, that the dataset has 41 features which introduce the connection type like TCP or UDP or the duration, and the details of the 41 features will be listed in the website. And there is one thing that I would have to mention here is the test data is not from the same probability distribution as the training data. And in fact, it includes specific attack types that are not in the training data. This is a very realistic problem, and that we may meet in the real practical problems that I will show you the details that how to solve this. And in detail, that the datasets have 24 training attack types, and there are additional 14 types in the test datasets that are not contained in the training data. Here I use the NSL KDD dataset instead of the raw dataset. I choose this dataset for 3 main reasons. The first one is that this dataset does not include redundant records in the training set, so the classifiers will not be biased towards more frequent records. And another reason is that there is no duplicate records in the proposed tests. Therefore, the performance of the learners are not biased by the methods, which have better detection rates on the frequent records. And another very important reason is that the number of records in the train and test sets are reasonable, because we remove the duplicates and thus we reduce nearly 1/3 of the dataset size, the size of the datasets, that will make it runnable on computers and may get a more reasonable results in a shorter time. So before I do the experiments, the very important thing here is data preparation. Here I use stratified remove folder to divide the training data into 2 sets. The cross-validation dataset contains about 80% of the training dataset that I use to make cross-validation and train models. And then the left 20% of the training dataset, I set it as the development dataset. And I use this dataset to do data exploration and error analysis. This is quite important because here I won't touch the final test set and only do the error analysis on the development data, and then I will perform the final algorithm on the test data, and to after the optimization that to perform the final result. Here you can see that I just simply use a naive Bayes algorithm to perform on the cross-validation data. The reason why I choose naive Bayes because after reading the papers, this is a very efficient algorithm that most scientists will choose for the KDDCup. And another reason is that naive Bayes is very reasonable for a practical problem because it has assumption on the probability distribution, which is true in many cases, and we get a accuracy of nearly 50% and with a kappa of 0.4. And you can see the configuration matrix here as is shown here. And from the configuration matrix, we can see that directly that the most error occurs in this normal part, that which the connection is actual normal, but we misclassified as different kinds of attacks. And we may solve this problem and go deep into this problem in the next step. So in order to addressing the missing label of the dataset, the first step is to assign different kinds of attack into one category that I call it attack here, and I use this new design dataset to analyze different machine learning algorithms. This is not the final result, but it's just a middle step that I use to analyze different algorithms and find what I need to improve here. So I just use cross-validation over the cross-validation data here, use naive Bayes, and significantly I get a 90% accuracy and with a kappa of 0.8. Actually, it is a very good result. And the configuration matrix can be shown here. So then I perform with the naive Bayes algorithm on the development dataset and do error analysis. And as you can see that the accuracy and the kappa is almost the same as the cross-validation. But from the configuration matrix, we can see that the bottom left is extremely high. That means many instances are classified as normal while they are actually attack. But here I need to, in this particular problem, that the test dataset is completely different from the training data. So I need to perform on the test data to determine an algorithm and to test if it is good. Here I perform the naive Bayes on the test data, and as we can guess, that the accuracy and kappa falls significantly. That from 90% to the accuracy falls from 90% to 76%, and the kappa is only 0.5. Actually, with a kappa of 0.5, it is already a good, not very bad algorithm. And the configuration matrices can be seen here, and we have the same problem that many attacks are classified as normal. Here, then I do some machine learning algorithm exploration and to and try some different kinds of machine learning algorithms here. Because this is the classification problem, and due to 41 features, so here a decision tree is kind of a reasonable guess algorithm, and here I perform decision tree here, and I get a, this is the result on test data set, the final test data set, and I got a 80% accuracy and with a kappa of 0.6, which is better than naive Bayes, as you can see. And then I further use the random forest. It's a little bit worse than the decision tree, but it's also much better than the naive Bayes algorithm. And the configuration matrix is shown as below here. But then we have to deep into this problem, that we only divide the label into two, the binary label that is the normal connection, and the tag is just the first step. We cannot just do this problem like this. So a reasonable approach is to assign all attacks into 4 main categories. This is shown that in the paper, the different kind of paper showing the same, and that in practical, these two categories that contains nearly all kinds of network attacks. So here I use these 4 categories. And the DOS is the denial of service. R2L is the unauthorized access from a remote machine. U2I is unauthorized access to local superuser privileges, and probe is surveillance and other probing. And then I dig into the training data and test data, and I guess the proportion of different kinds of attack categories. As you can see, that in the training data, most of the instances is labeled as normal and DOS, and there are 9% of them as probe. Here's a typo here, this should be probe, and the other 2 categories is very small portion. But in the test data, as we can see that although normal and DOS are still two main categories, but the R21 and probe is much higher than the training data. So from these two, we can see that the test data, the distribution of different kinds of attacks in the test data is different from the distribution in the training data. And using this 5 label classification, I do cross-validation over the cross-validation data, use the naive Bayes as I stated before, and I got the accuracy of 80% and a kappa of 0.7. And with the configuration matrix here, we can see that this is not a bad result. But and if we perform naive Bayes on the development data, we get an accuracy of 84% and a kappa of 0.7, and we can see the configuration matrix here. And we do error analysis on this configuration matrix, and we can see that the diagonal means that we classified correctly, and we can see that this line has these values should be 0, but actually they have a much bigger values. That means that many instances are classified as different kinds of attacks, while they are actually normal, because here, as we shown. This is a little different from the error that by the binary classification as I stated above previous. So it's a little different. And then I perform the ABS on the test data, and I get accuracy of 70% and a kappa of 0.5. So you can see that here the accuracy and kappa is not as good as the result by the binary classification. But this 5 labeled classification is much closer to the practice, to the real situation. So we cannot just say that this 5 labeled classification is wrong, because this is the reasonable, while the binary is just the first step and a guess. So we can see the configuration matrix is here, and here we can see another problem, that you may find that this value is very large. So actually, the many actual DOS attack instances are classified as normal, as I shown here. Then after that, I do a machine learning algorithm exploration that use different kinds of machine learning algorithms. From the experience above, that I still use the decision tree and random forest, because in the binary classification, these two algorithms have a good performance, better performance than AEVS. And here we can see that the decision tree truly have a better accuracy and kappa here, with a 45% and a kappa 0.6. And here random forest have an accuracy of 78% and kappa of 0.65, and with both configuration matrices of these two algorithms. But here is a very important step, that is random forest really better than an AEBS, the baseline? Because we cannot just say that the average accuracy is better than one algorithm is better than another. So here, actually, I use stratified remove folder to divide the training dataset into 5 parts, 5 subsets, and with each subset contains about 20% of the original training dataset. And I did the same thing on the test dataset, with each subset about 20% of the test dataset. And then I train on the subset of the training data, and then perform the result on the subset of the corresponding test dataset. So here I get a 5 performances. This is the first, I train on the first subset and test on the first subset of the test data. And this is the second, the third, and this is the accuracy actually of the non-UBS algorithm. And here in the second row, I show the accuracy of the file folder of on the random forest algorithm. And then I do a pair t-test, that I got a p-value of about 0.113. And actually, we can see that one algorithm is significantly better than another if the p-value is smaller than 0.1. And here I get a p-value about a little larger, just a little larger than 0.1. So we can still treated as a significant improvement here, so I will choose the random forest as my final algorithm. Here I will state that just as I stated above, that the test data is significantly, the distribution of test data is very different from the distribution of the training data. So here we actually get a very high variance. So the important thing here is that how to fix this high variance. The first step is to try to small set of features, because here we get a 41 features, and actually this is very large, and some of the features is correspondingly less useful. So we need to reduce the feature space to reduce the variance. And another thing is that we need to get more training examples. Here in the dataset, that the training examples is, the training data is about the 2 times of the test data, but maybe it is not very sufficient for that. And actually we can see that there are some attack that did not even exist in the training data. So we need to get a little more training examples that reduce the high variance. And the third method to fix the high variance is increase the penalty of weights. Here I mean when do regularization of the weights, that we have to introduce a penalty of these weights, and by increasing the penalty we can fix the high variance. Also, there are something that, just as stated above, the test data has many attack types that don't even exist in the training data. So I come up 2 ways that may solve this problem. The first one is k-means cluster. The idea that I thought is that I group the attack into 38 clusters, because there are totally 38 attack types that we already know, and then we represent each of the attack instance by cosine similarity with each one of these 38 centers of these clusters. And by this way we can replace the original dataset, the attack instances in the original dataset, into only the 38 features of instances, and by doing machine learning algorithms on this new dataset, we may find the corresponding attack types of each instances. And another method to solve this missing label is that PCA, the principal component analysis, that we will analyze the principal component of missing label instances and classify based on these components. That may be, but due to the time limitation, that I have not performed these 2 algorithms on the Hadoop, that may be treated as future work in my further step here. And thank you very much.